So we know that the posterior distribution is going to be determined by the balance between the strength of the prior and the amount of data. So this video is all about the strength of the prior, and I'm going to consider three broad categories, starting with the flat, going to the weakly informative, and then finally the strongest, the informative. So we begin with a flat prior and return to the globe tossing experiment, where we're trying to determine the proportion of the Earth's surface covered by water, which is the equivalent to the probability that a randomly selected point on the Earth will in fact be water. We're going to start off with the assumption that there are only 5 possible values for this thing theta, the proportion of the Earth covered by water. And then we're going to assign our priors to those theta. And with a flat prior, what I'm going to do is assign the same value, 0.2, to each one of these different values of theta. So in other words, in advance, I know that one of these things is the true proportion of the Earth covered by water, but I have no idea which one of those it actually is. So once I've got my prior, I now want to go through the normal steps that we would use in order to calculate the posterior. So the first thing we need to do is evaluate the likelihood function. Remember two things about the likelihood function. First is that it reflects the process that gave rise to the data. And secondly, the data are kept constant, and the value of theta, the parameter, varies. So the process that gave rise to the data, the globe tossing experiment, meets all the criteria for a binomial process. There is the binomial distribution. The data will be kept constant at 4 successes in n trials, and then in succession, we will take each one of these values of theta, put them into the likelihood function, and evaluate the likelihood. Next thing we do is we take the prior, we multiply it by the likelihood, like this, multiply each one of those across. What do we get? We get this thing. What is this thing? This is the joint probability of theta and the data. We sum up all those joint probabilities. What does that give us? That gives us the marginal probability of the data. If we then take each one of these joints and in succession divide them by the marginal probability, that gives us our target, our goal, the posterior distribution of theta. So think about what happens when we use a flat prior. Each one of the values here, each one of these joints is arrived at by multiplying the corresponding likelihood by the same value, by a constant value. And as a consequence, when we take each one of these joints and divide it by their sum to arrive at the posterior, what's going to happen is, if you think about the relative size of the values in the posterior, they're going to be exactly the same as the relative size of the values of the likelihood. And in fact, that's what I did for the last column. For the last column, this column here, all I did was take the individual likelihoods, divide those individual likelihoods by their sum, get these values here, which are exactly identical to the values that I got when I obtained the posterior through the normal process. So the whole idea of a flat prior is that we assign the same prior probability to each one of these values of theta. And as a consequence, the posterior is determined entirely by the data. It's determined entirely by the data as it's put into as the likelihood function is involved, and as a consequence, the data are allowed to speak for themselves. Now what I want to do is talk about diffuse priors. And diffuse priors reflect a higher uncertainty about what the true parameter value actually is. They're not completely flat, but they are relatively flat. And as a consequence of being relatively flat, the posterior is going to overwhelmingly be determined by the data. There isn't going to be much effect of whatever it is we choose as our prior. I'm going to do this by example, and the example involves the mean or average IQ of international baccalaureate students. In other words, students that are enrolled in this academically rigorous program. Now, if we think about the population as a whole, not the IB students, but the population as a whole, IQ is deemed to be normally distributed with mean 100 and variance of 225. So we sample 9 of these IB students and find out that their mean IQ is 111. For our likelihood function, we're going to use a normal distribution. We're going to have a mean that's equal to mu. And this mu is what we're interested in. This mu is what we want to get the posterior of. This mu is the mean IQ of the IB students. And we will assume that the likelihood function is going to have a variance of 225, the same as in the general population. And then we're going to compare 2 different priors for mu. And one prior is going to have a mean of 90, and the second is going to have a mean of 140. And the reason for choosing these 2 values is if I think about what the mean IQ of the IB students would be, it would almost certainly lie within this range. The key is that we're going to have a diffuse prior because we assign to it a very large variance. So here we have one prior. Its mean is equal to 140, and its variance is equal to 1,000. And this solid line here reflects the posterior. And this vertical line reflects the data. In our sample, the mean IQ was 111. In this second plot, now we have our prior, and the mean is only 90. The variance remains at 1,000. And look what happens. There's very little change, very little difference in the posterior here and the posterior here. And irrespective of this big difference in means, you can see that the mean of both these distributions is essentially reflective of the data. So that's the idea of a diffuse prior. And now what I want to do is go on to the strongest category of priors, the informative prior. So the whole idea about the informative prior is that we have prior knowledge, and we're going to deliberately use our prior knowledge to influence the posterior. Now, critics might say that, this is kind of sketchy because it permits subjectivity on the part of the researcher. It potentially allows the introduction of bias. So, a researcher might simply decide that, okay, I'm going to choose as a prior something that will give me a posterior that supports whatever story I want to tell. So I want to push back on that idea in a couple ways. And the first way is to say, okay, let's not kid ourselves. The kind of analysis that we do as frequentists also involves high levels of subjectivity. So I'm just going to go through a very quick list of things that are subjective. I'm going to say it in the context of frequentism, but many of these issues also arise in the case of Bayesian analysis. So, where are some subjective choices? If we've got multiple dependent variables, do we use multivariate analysis or do we use separate univariate analysis? If we've got a nonlinear function, do we use general additive models or nonlinear? Do we use parametric versus non-parametric? Big question is that of model fit and selection. How do we deal with collinearity? If we've got a whole bunch of variables, do we use ridge regression or lasso regression? We've got multiple competing models. How do we select among them? AIC, BIC, CP, just R-square, or any other number of different things we could use. Oftentimes, when we have a particular method of model selection, we'll discover we've got different models, different parameterizations that have similar goodness of fit. How do we choose among them? And then finally, something I've played around a bit is looking with outliers and perhaps more importantly, influential points. And we oftentimes don't look at influential points. I think a couple of reasons for that is it's a bunch of work. And also, having played around with that, sometimes when you actually look at influential points, it gets a bit scary. So it's better, easier just to ignore that. So frequentism does have elements of subjectivity too. There are, however, some benefits from using prior knowledge. And one way to think about that is it enables us to integrate results from different studies. So if you think about how we present our results when we write papers. So we'd have an introduction, then we'd have our stuff, and then we'd have a discussion, and then we'd explain how our results fit in with prior knowledge, prior studies to move knowledge forward. But this is a rather informal process. Might there perhaps be a more formal, a more quantitative way to combine our work with previous work? Well, one way to do that is meta-analysis. And Bayesian analysis has been used quite effectively for meta-analysis. My sense, however, is that for environmental or ecological studies, that meta-analysis oftentimes isn't going to work because there's heterogeneity both in content and, context, quality among the different studies. So, as an alternative, maybe what we could do is think about previous work that's been done, take that work, translate it into informative priors, combine it with our stuff, and get posteriors that take advantage of that previous information. And that's what's done in this paper that's shown on eClass. Another possible benefit is it enables us to leverage expert knowledge. So there's a study done by these folks. You're looking at survival, I believe it was, of ticks. And they used a Weibull function for survival. It had two parameters, lambda and p. And so for lambda, there's lambda, nonlinear function, and the predictor variables were q and u. And what these folks did was they talked to a bunch of experts, got some prior values for these different parameters here to get an improved model. So, in summary, strength of the prior is going to be really important in determining the posterior. So, as you read papers, focus on the strength of the priors that we used and also the justification for those priors.